Okay. Alrighty, we will get started today with continuing on our discussion. The last little bit on sustainability and wrapping up some cost discussions of sodium-ion batteries, leading into lithium sulfur batteries, which will then get us to the next two sets of modules for lithium-ion alternates. So we left off discussing the replacement of materials for lithium-ion batteries versus sodium-ion batteries. And we highlighted the advantage of going from lithium-ion using copper and aluminum anodes to sodium-ion batteries, and the advantage of just using aluminum foil for the anode, because now there's no alloying reactions that you have to think about. So that's why the copper foil is voided out here. So that is an advantage, but the thickness of the current collector increases. Oh, sorry, I said anode, I meant current collector, aluminum current collector, not aluminum anode. Aluminum current collector is a little bit thicker in the use of sodium-ion batteries versus lithium-ion batteries. So, so it's a little bit thicker, but the offset is that the price is, cheaper. There's less of a price fluctuation. So a number of advantages there. We also left off talking about comparing current technologies of cathode as well as anodes of synthetic graphite. And then we talked about, looking towards the future and if sodium-ion battery technology can be improved so that the energy capacities increase as we develop more of the electrochemistry and also the chemistry of the materials themselves. And so we talked about this NMC 622 going into the future using natural graphite and also this advanced carbon and using with phosphorus and hard carbon composite. Now, these futuristic or advanced and futuristic models are really averages of the current state-of-the-art capacities that can be achieved. So, for future materials, it's sodium vanadium phosphate, maybe with a little bit of oxyfluoride in there, fluorinated sodium vanadium phosphate. So when the denotation is some futuristic material, it's not that the material doesn't exist, it's that the numbers are sort of average to sort of predict what is the likelihood of the capacities that can be achieved and improved upon in the near future, and how does that impact the overall costs of the sodium-ion batteries. Okay, so in terms of breaking down, how these comparisons are made and where the costs are derived from, there's always a trade-off. So when you go from synthetic hard carbon, the trade-off there is the capacities that decrease a little bit down to 300 milliamp hour per gram versus synthetic graphite, which is 360 milliamp hour per gram. And in terms of reduction in costs of the cathode, you see currently the cathode would cost less, a sodium manganese oxide, say, at $7.60 per kilogram. And that's, over the current price for lithium-ion battery cathode, lithium manganese oxide to be specific, at $10 per kilogram. So there are some decreases in cost of the active material, but in terms of the overall cost, the new electrolytes that have to be synthesized, the cost of NaPF6 in equivalent carbonates of the solvent in the electrolyte, the cost does go up a little bit, and you have to now, even though the cost, let's say synthetic hard carbon, the capacity is a little lower, so you have to use a little bit more of the material to have parity with the overall capacity at 300 versus 360 milliamp hour per gram. So all these offsets are taken into account when calculating the overall cost of the entire cell, not just the active material itself. So in the future, there is potential for pretty close, parity between lithium-ion batteries and sodium-ion batteries. The cost for this, fictitious averaging of NMC622 and some silicon carbon anode. Actually, that's this phosphorus, but that's a copy and paste. That should be silicon carbon, but oh, that's for lithium-ion batteries. Sorry, no, that's correct. So anyway, that's all to say, these are models. They could obviously change. This paper is already a few years old. So these cost models could change, but this is a good exercise in really breaking down the components and really trying to tease out, what is the driving motivation for any new technology that's worth exploring. Just because a material happens to be earth abundant, doesn't always mean that the overall costs of the active materials as well as the cost of the cell will always be lower. Because electrolyte development is also really key in obviously making the batteries work, but also affecting the overall costs of new technologies. So, but that's all to say, just because something's new, or the cost increases or cost decreases are not so readily apparent, the environmental factors when it comes to sustainability also are important. And in terms of energy demands, that's something we also need to think about, where the impact really is. So here, in terms of lithium carbonate extraction, we talked about, lithium salts coming from Chile, a huge producer of these salt vats, these salt brines that, that the lithium salts are taken from. Now, if we move to, let's say, extraction of sodium salt for the sodium-ion battery electrolyte, we'll see that we can actually get much more sodium salt coming from the same salt flat in Chile, the Atacama salt flat. Now, does that solve our problem of having these huge flats in Chile and the amount of time that it takes to evaporate the water and then purify the salts? No, but you can get now 2 salts from the same location. So that's, somewhat promising. Can you also get salt, sodium chloride and lithium chloride out of the ocean? The answer is also yes, but they're the ocean is vast, obviously. But in terms of getting lithium chloride out of the ocean, the concentration there is so low that's actually quite energetically expensive and costly to do so. Now, in terms of impact, while there are many more devices, portable devices, than there are, let's say, the needs for electric vehicles, plug-in vehicles, all electric, battery electric vehicles, and then also larger trucks and households. While there are a lot of devices, in terms of energy demands, the overall demands are not going to be as much as, producing battery chemistry for electric vehicles, household electrification, and large truck electrification. So that's where the impact really is going to lie in terms of the future. Okay. So with that, we jump over to discussion of lithium sulfur. So my intention for discussing lithium sulfur cost and sustainability is to really show you all explicitly how detailed these calculations can be, particularly because, one, this is the type of exercise we need to do whenever discussing sustainability of new technologies, but also this methodology will be useful for your sustainability assignment as well. Now, we talk about sulfur and its advantages because it's readily available, it's quite cheap, and that we can see. In terms of fractions of the Earth's crust, it's relatively high compared to the transition metals, 3D transition metals here. In terms of cost, you could see here per pound, US dollars per pound, it's like $0.001 per pound relative to, let's say, $10 per pound for cobalt. And that's just the minimum, okay, minimum values in the range. So that's, that's pretty attractive. And one of the reasons why the sulfur cost is so low is because it's a derivative of petroleum refining. So you can see here sulfur being used in a battery in this schematic, mixed in with carbon. I have to say, I made this figure 7 years ago, and it's still paying off. So you make a figure once and you copy it for the next 7 years. Never make a figure more than once. So what you see in the photo, though, is here are these just mounds and mounds of sulfur. This happens to be in Vancouver, British Columbia in Canada. And as a result, from petroleum refinery, that's not going anywhere anytime soon, in the near future anyway. And so, petroleum, so from the refinery process, we can get a lot of sulfur out, which, drives down the cost quite a bit. And, even though sulfur is heavily unwanted in petroleum, now as a byproduct, it's quite useful to make cathode composites for lithium sulfur batteries. And in terms of, world production reserves, there's plenty of it out there. There's not, it's not going anywhere anytime soon. Now, the chemistry that we'll be talking about is quite different for lithium sulfur batteries versus the lithium ion batteries that we talked about, right? So in terms of the number of moles of lithium ions that can be transported, you can already see here that it's quite a lot. So it's more than, let's say, 0.5 molar equivalent for lithium cobalt oxide for intercalation-based mechanism. So conversion-based mechanism does offer transport of more molar equivalents of lithium ions, which increases the energy density. But the electrolytes are also quite different. So from what we've talked about previously of, typically 1.2 molar LiPF6 in ether-based carbonate-based solvents. Now we're talking about ether-based solvents. So the challenge here is the solubility of sulfur in the lithium polysulfides in these electrolytes. So what we'll be focusing on is how to achieve parity with, let's say, lithium metal batteries, let's say with NCA cathodes, or lithium ion batteries with graphite even. So we'll focus on the electrolyte to sulfur ratio, because right now that ratio is quite high. If you want to have a lean process where you try to reduce the amount of materials that you need to basically the bare minimum to cut costs, you're going to have to bring down the electrolyte to sulfur ratio, because you need higher electrolyte concentration or loading to dissolve the sulfur. Okay. So our targets here, right, if you have a theoretical capacity of about 1600 milliamp hour per gram, if you can achieve 75% of that, that's about 1000 milliamp hour per gram. Okay. And if you can get up to 5 milligrams of sulfur loading per centimeter squared of your electrode, then that's pretty high as it is. Now you could see that at the anode side, we have lithium metal, and with all batteries thus far using lithium metal, you need lithium metal anode protection, right? This is not just for lithium sulfur, this is for all batteries that have a lithium metal anode. Protection is the key thus far. And so either you can have, a physical material that protects, like, solid electrolyte, or just like your usual separator. But what has been seen in lithium sulfur is that just having a polypropylene separator does not do the job. And there are several hundred studies that show that, with all sorts of physical barriers that have been added to prevent the polysulfide shuttle, which is exactly shown in the orange arrows that you see here, right? So you have, once sulfur is added to, it is in the composite cathode. In ether-based electrolyte, you have polysulfides, and you also have the production of lithium polysulfide. And these two species, or sets of species, will migrate. They will shuttle from the cathode over to the anode, sometimes get deposited on the anode, and you form solid electrolyte interfaces that are not always advantageous. You also lose active materials. So the research thrust behind, prevention of polysulfide shuttling for the last 20 years has been on that. Many things have been tried. Not everything has been that successful. And it really comes down to comparing apples to apples. Just because an additive works at a certain sulfur loading or a certain electrolyte loading doesn't mean it translates when you try to increase the sulfur mass loading. It's a totally different ballgame when it comes to solubility of sulfur and lithium polysulfides and the polysulfide in the electrolyte and in the catholyte. So it's all very nuanced, and the parameters change. So I'll go into exactly the ranges in which, lithium sulfur could be competitive. So Brian McCloskey has done a really fantastic study on calculating, the parity achievement values for lithium sulfur as compared to lithium ion and lithium metal cells. And the configurations are shown here. So lithium ion battery with graphite is similar to that of lithium metal batteries with lithium metal anode instead of graphite. But the difference here, what you'll see is, instead of just an electrolyte wetted cell guard, polypropylene separator, you have now an addition of solid separator that can be anything. So he's looked at LATP, LLZO, and also LPS, lithium thiophosphate base separator. And then when it comes to lithium sulfur cell, so it's quite similar to that of the lithium metal battery. You also have a physical separator here, but the sulfur to carbon to binder ratio is really dependent on what you're trying to achieve. If you're trying to increase gravimetric capacity or you're trying to increase volumetric capacity, it's a different ballgame, depending on what your objectives are and how you load the cell. Now, it's, in terms of comparison, it's pretty straightforward in terms of calculating the gravimetric capacity and also the volumetric capacity, right? So for gravimetric capacity, you just take, what is your average cell voltage, you multiply it by the active mass loading times the active mass, active material capacity, and then divide that, if it's gravimetric, right? Then you divide that by all the components, the mass of all the components. It is really that simple. In terms of volumetric, you divide by the density to get the volume, but it's just that. So now this takes into account all the materials, not just the active material that we've been talking about before, but the mass of the current collector, the mass of the separator, the mass of the electrolyte wetted cell guard separator, all that. So it's quite parametric, and it is, a very useful study to analyze. And he has an accompanying Excel spreadsheet, so you can play to your heart's content. Now, the ultimate question we want to ask is, okay, how do I design lithium sulfur so that I use the least amount of sulfur, but I load just enough so that I can get as high energy density as I can while minimizing, all the other costs, protecting the lithium anode and all of that. So then the first question you have to ask is, well, how thick of the separator do I have to protect the lithium? So the first order of business is to compare a lithium ion battery with a graphite, or C anode as denoted here, to that of lithium metal. So if you assume 17 milligrams of per centimeter loading of NCA, so you use something that's state of the art, which in 2015 was a reasonable choice. So if you assume 17 milligrams per centimeter loading, and you say, okay, well, if I don't have any separator thickness, right? I don't have a separator to protect the anode. Of course, my energy density is going to shoot up extremely high. Great. But then your cell's also going to fade extremely fast. So if you increase the solid separator thickness, where will you break even? To compete with that state-of-the-art lithium-ion batteries with a graphite anode. So that's what's done here. So as you increase the thickness, you can see here, you can get out to 100 micrometer thickness of the separator to then achieve parity with lithium-ion battery with a graphite anode that doesn't need an additional separator for lithium metal protection. Okay. And in terms of the choice of the separator, it depends. So if you choose lithium polysulfide versus LATP versus LLZO, they have different densities, and thus the different thicknesses will also have different mass, which will then affect your overall capacity. And so what you see here is, depending on the NCA loading, you're going to need different thicknesses and different amounts of protection, because you're going to have different amounts of lithium that you need to protect. So the break-even thicknesses will change as a function of your mass loading for your cathode as well. Okay. So then how do we calculate all of this? So in terms of the numbers that have to be crunched, the salient numbers that have to be crunched, ultimately what we want to know is, what is the gravimetric energy of the cell? And how do we input that in terms of each component? And we will do so similarly for lithium sulfur. So for a lithium metal battery cathode, what you see here is you need to put in, well, we want to know what is the energy of the cell. So that's the watt hours per kilogram. Well, we know what the mass of the, the components are, and we can get all of that from here. The energy of the cell is pretty straightforward. It's just the average voltage of the cell times that of the capacities. And here we're normalizing by the area of the capacity. Okay, so the amount that's in per centimeter squared of the electrode. And the voltage, the average voltage is just taken as the average of the discharge and the charge. So that's pretty straightforward. The mass of each component can be broken down into, well, all the components within the battery. So here you see the current, the copper current collector with a thickness of, let's say, 4 micrometers. You can just go down the list. You can put in the active material loading, how much of the NCA is in the cell, and of course with the with electrode design, right? You don't have just active material, because these are semiconductors or insulators, and thus you need to improve the electrical conductivity, particularly for sulfur as well. So there's going to be some amount of carbon additive that's going to be added to your cathode. There's also going to be some binder percent that's going to be included in your cathode composite. The amount of lithium that's in the cell, so that's going to be based on the amount of cathode that's loaded. Electrolyte weight in the cathode, so you have to wet your cathode as well. Your current collector, for the cathode and the anode. That's pretty straightforward. Binder and cathode separator, and then the solid separator mask, which is not a component if you don't have to, if it's a lithium ion battery with graphite anode. So, this is really just to demonstrate the arithmetic that goes on when you have to calculate to get the mass per centimeter squared, right? So if you have the thickness of your current collector and its density, copper or aluminum, you can calculate out, the grams per centimeter squared that way. The solid separator, similarly, the thickness that you put in, you then multiply that by the density of the material that gets out the mass. The amount of lithium convert to grams per centimeter squared is done so here. And then similarly, the amount of carbon or binder that's in your cathode, you can also calculate by just, the weight percent that is used. So it's pretty straightforward, but it's, organized in a useful spreadsheet. So I would use that if I were you, because it's a good launching point for performing these types of calculations when you want to make statements like, using this material will improve the cost by X, or, will increase the capacity by Y. It's a pretty organized. Obviously, you can also make your own spreadsheet and crunch out these numbers. But FYI, there is a spreadsheet out there already so that you don't have to reinvent the wheel. And it's a very useful read because it's the type of comparisons that we need to make. These are the kind of calculations that one needs to make to really compare apples to apples. In terms of the energy, the specific energy that can be achieved in these lithium sulfur cells, it really depends on your assumptions of the amount of sulfur that's utilized, right? Similarly to lithium ion batteries where you load NCA or NMC or LMO, right? There's a percentage of that material that's active. That's useful, as in you can utilize that. And for sulfur, the aim of 70 weight percent of sulfur, using 75% of that is pretty desirable. I mean, that's a high target already. And in terms of the electrolyte to sulfur ratio, what we really need to do is bring it down to 5.3, because right now typically these batteries are, the demonstration batteries like point cell batteries are really drenched so that you get the liquid electrolyte permeation into the cathode composite to really run the cell. But when it comes to commercialization, you really need to have a linear process where you bring down the electrolyte concentration, the electrolyte ratio. And so what you see here is, in order to, if you have high electrolyte to sulfur ratio, let's say 10, something quite high. So you have 10 microliters to every, milligram of sulfur, you have less active material, and thus your specific energy goes down and your energy density also goes down. So watt hours per volume of the cell also goes down as well. So in terms of competing with lithium metal batteries or lithium ion batteries with graphite anode, what we're really looking at here is, in terms of sulfur mass loading, we're looking at something between like 9 and 10 milligrams per centimeter squared. If you don't have a feel that for how much sulfur that is extremely high mass loading. And on top of that, if you're at that high of a regime, you now are running into solubility issues, in terms of mass loading for sulfur. So it's quite a balance, in terms of, if you want to achieve higher specific energy, yes, you use less electrolyte, but is that going to contribute to capacity fade because, in performance of the battery, just because there isn't enough electrolyte there, to actually run the battery. Now, in terms of the cost comparison, So here we're going to look at the separator. If you look at lithium battery with a graphite anode versus lithium metal anode with the same NCA loading. So here, you have 3 milligrams per centimeter squared, 8, 16, 33, you get increases in specific energy. So where is there going to be a comparison? Where is there going to be a parity in terms of the cost of the separator to make lithium metal batteries competitive? And we're looking at about somewhere between $2 and $5 per meter squared of the separator, assuming, let's say it's LATP, for lithium metal batteries to be competitive with that of current state-of-the-art, graphite anode in lithium-ion batteries. Okay, so it's about actually maybe $350 per meter squared. Okay. In terms of comparing that with now lithium sulfur battery technology, you see here the same curve is applied for lithium-ion batteries with graphite anode. And what you see is, depending on the sulfur loading, between 1 and 15 milligrams per centimeter squared, if you want to achieve parity here, we're really looking at, bringing the cost down to somewhere between $5 and $10 per meter squared of the separator, right? So that is achievable, but it's still pretty high. And that assumes these, idealized numbers of electrolyte to sulfur ratio of just 2, so relatively lean, 75% utilization. So the amount of sulfur that you put in and how much of the capacity you can get out is 75%. So 75% of what you actually put in terms of the electrode. So these are pretty high metrics for getting lithium sulfur to be competitive with that of lithium ion batteries with a lithium metal anode and an NCA cathode at 17 milligrams per centimeter loading. Okay. So in terms of calculating the costs, so this is all based on the backpack, although those are from 2012 costs, so you should update your costs with the 2019 backpack model, out of Argonne. So this is the model that's in the 3rd iteration now. So the 2019 report is the 3rd iteration, although you'll find the 2012 out there as well. And so the prices do differ a little bit, and in the 7 years that these 2 reports have come out. But in terms of calculating the cost per kilowatt hour, that's what you really want to bring down at the end of the day, right? For consumer applications, the cost, especially for electric vehicles, the cost really has to come down to about $100 per kilowatt hour. And so you can reduce that cost by basically reducing the cost of your overall cell, but particularly the cathode. The cathode is where you're going to drive the cost down quite a bit. And so we'll talk about that in terms of driving down the costs, but also if the cathode is a key component of the cost, then it would be worth it for us to think about the recycling of these materials, or at least just salvaging them and reusing the batteries for different alternatives. Because if we're at 2022 and by 2030, that's about 8 years, that's within the shelf life of all of these battery materials. We have to think about what we're going to do with these batteries in the next 8 to 10 years. So in terms of recycling, getting the materials back to either the metal state or the oxide form requires a lot of energy and also costs. So, the discussion of should we recycle? I mean, we should always try to reuse, yes, but what is, the quantitative comparison? What's the quantitative metric for comparison? It usually comes down to cost and energy. How much effort do you have to put in to get the material back, and then also to regenerate the pristine form? You know, if you want NCA back to its form, how do you recover that when it's fabricated in, you know, in an electrode that has carbon binders, that has polymeric binder, carbon additives and polymeric binders? The energy that it takes to get your active material back out is really costly. And thus, you know, keeping up with the number of batteries that are produced is extremely difficult. So in terms of the techniques that are used, you know, the three common ones are smelting. So that's pyrometallurgy. You basically just burn, you know, your electrode and then try to recover the oxides that way. You could also dissolve your composite in acid. So that's hydrometallurgy. Also, that requires some pressure. You can dissolve the material out. You can also try to precipitate out the material as, you know, just run a chemical reaction and get the salts back out. But that requires a lot of solvent. And then what are you going to do with the solvent? It's spent solvent. So, you know, that has its own issues in terms of recycling those solvent. And in terms of, you know, who's leading the way, CATL is a huge producer, but also a huge recycler of batteries. And if you look at the numbers of batteries that they've recycled within the last year, it's about 120,000 tons, which is equivalent to 200,000 cars. Now let's go back to our projected number of 60 million cars by 2040. So that's three orders of magnitude difference if you're thinking about recycling, right? For every year that you sell 60 million cars, in 8 years' time, you have to now start dealing with the batteries that are coming out, and maybe even 2 times that, right? Because a lot of the electric vehicles require two battery packs in their lifetime, in the lifetime of the electric vehicle. So, I mean, it is quite an issue that, you know, people are dealing with. Now, I've listed some other strategies here because, you know, just burning material doesn't have to be the only way. There are promising strategies for, let's say, digesting not just the metal, but the polymers. So instead of just burning and digesting out the polymers, you could think about enzyme digestion. And so that's a hot area of research as well, getting enzymes to eat your polymers for you. Okay. Now, in terms of policy wise, there's a lot of driving force behind policies that will encourage countries and, you know, continent, you know, to recycle. And so here you see different scenarios about how to approach sustainability. So we could think about, well, we can do nothing, which is, or, you know, just keep the status quo, which is some recycling, but not that much effort. And so that's the reference point here. You know, there's a lot of batteries that are just not recycled, go missing, they're unaccounted for, who knows, maybe they'll end up in the landfill when they shouldn't be, all of that. And in terms of, you know, strategies for either replacing, just taking back the batteries and then repurposing for another application without digesting any of the materials or restarting, you know, burning the material from scratch, that can also be quite useful. Now, the point here is that when we think about cobalt reduction, we often think about, okay, well, what are we going to replace cobalt with? And thus far, the technologies have been high nickel or lithium iron phosphate or NMC type materials where you have high nickel loading. So then you basically just push off the energy requirements for cobalt to now nickel. Okay, so then we have to have a discussion about, you know, where nickel comes from and how to process nickel, but that's also, you know, something that we have to discuss down the line. In terms of energy demands, I want to talk about, you know, talk about and compare the two methodologies for recycling. So I've mentioned hydrometallurgy and also pyrometallurgy, and I put a link here for that has a helpful video for actually showing these methodologies. But the takeaway is, are we ready? In terms of these two methodologies, it takes quite a bit of effort and also time, right? In terms of hydrometallurgy, this method involves, mining, crushing the material, agglomeration of the materials, heap leaching. So basically you have a vat of this dirt that you have acid in there, and it just leaches the material, the metal of interest out over time. Then you have to extract the solvent out, and then you have to electroplate the metal that you want, on, so that you have this now gigantic ingot of the metal that you want. Okay, so that takes time and extremely a lot of energy. Pyrometallurgy is similar in terms of, mining the material, crushing, ball milling it out, thickening, filtering, smelting, bringing this, the ore up to, or the material, if you're recycling, up to high temperatures, right? So in terms of now thinking about extracting your active material out of the composite and taking it through these two type of processes to get back to the metals or the metal oxide is extremely challenging. And that is if you have pristine materials. If you have defective materials because of cycling over time, you have metals that are in the anti-site and all of that, right? Then you have, well, less yield than what you would expect. But it's still pretty, advantageous to think about recycling, because here you could see in terms of, the greenhouse gas emission per kilowatt hour of an NMC battery. If you look at the number of kilograms of CO2 equivalent that's produced, the cathode itself takes a huge portion. Cell manufacturing also takes a huge portion, but the cathode alone produces a lot of CO2. So if you can, CO2 equivalent. So if you can recycle some of the material, you can potentially cut down the emissions. So then the natural follow-up question would be, is it advantageous to do so? Is the amount of CO2 equivalent, the number of kilograms of CO2 equivalent, would that actually decrease? Well, potentially. It depends on your cell chemistry. It also depends on your cell geometry. So the question that someone posed at the beginning that asked, are we going to talk about, if we should fabricate, what's advantageous, a pouch cell or cylindrical cell or whatever? And I said, no, we're going to talk about materials chemistry only. Yes, there's a tinge of that, but when it comes to sustainability, one does have to think about the geometry in which, the cell configuration is going to be in. So here you see a comparison from 3 different sources, national average, this group called the Northwest Power Pool, and then another corporation in Michigan, in terms of tabulating how much CO2 equivalent is produced. And what you see is the emissions for these 3 sources will vary, but what you see for cylindrical cells versus for pouch cells, you see that pouch cells have an advantage for decreasing the amount of CO2 equivalent when it comes to lithium iron phosphate chemistry. Okay, in terms of cell manufacturing and also overall CO2 emission. But pouch cells are higher relative to cylindrical cells when it comes to the other 2 chemistries, so the NMC and NCA chemistry. So it depends what chemistry you're targeting, if the CO2 equivalent is going to be increased or decreased for the 2 configurations. And then once you have these cells, in terms of recycling them, it's also a different story. So if you look at the emission, the amount of CO2 equivalent that's produced for NMC, NCA, and LFP in cylindrical versus pouch cell, or recycling, if you go through the pyrometallurgical or hydrometallurgy or just direct recycling, so that means you just take the battery out and you pop it in something else. If you look at LFP, you see here, okay, direct recycling interestingly enough, there's an increase in emissions of CO2. And if you ask yourself, well, is there a gain? Do I reduce the amount of CO2 if I recycle LFP cells? What you see here is the emission avoided is actually negative. So why is that the case? That is because iron already avoids some of the CO2 emissions, the higher CO2 emissions from relative to that of cobalt and nickel. So then when you try to burn or recycle iron, the amount of energy, the amount of heat, the amount of electricity that you have to put in to burn all of this stuff, or acid leach or what have you, you actually you don't avoid. So you're putting in so much energy to recycle lithium iron phosphate that you don't actually reduce the amount of CO2. You're actually contributing more CO2. Okay. Right. So let that sink in. Okay, based on this model, let that sink in. The amount of greenhouse gas emission is actually not avoided because you're spending so much energy and you're producing CO2 to burn and incinerate all the other stuff that's in your battery as well to try to recover the LFP active material. Okay, so these are the kind of quantitative metrics that we're aiming for when we talk about sustainability, and not make blanket statements like recycling is good. Okay, most people would not argue that recycling is bad, but in terms of quantitative metrics for the advantages of recycling, let's say NMC and NCA, there are huge advantages, when it comes to, let's say, CO2 emissions that are avoided, even though you have to put in more effort to try to recover NMC and NCA. Okay. Okay, so this caps my discussion of sustainability. We're going to go over now and continue with sodium-ion battery materials. Okay. So we go back now in time. We've been talking a lot about models and things that are going to happen in the future, near future, in fact. But when we talk about sodium-ion battery materials, we really go way back in time to the 1960s and even earlier, and talk about the solid electrolyte, the material that has dominated sodium-ion battery technology, and that's beta double prime alumina. This material is a fantastic solid ion conductor. Okay, if you look at here in terms of chemical stability, the diffusion coefficient, if you look here, the diffusion coefficient is extremely high, right? It's 1.7 times 10 to the minus 7 centimeters squared per second, and that's at room temperature. And that is like orders of magnitude more than any of the lithium-ion diffusivities that we've talked about before. It's also a really attractive material. It has high melting point, stable up to 2000 C. It's resistant to molten salt, so now you can run molten salt batteries at higher temperature. So it's fantastic material, and the technology is mature. It's very well understood, very well studied. There's decades and decades worth of data out there. And so the two technologies that use these types of materials for fast ion conduction and charge storage is sodium sulfur batteries. That also goes back several decades, and also the Zebra battery. So it's a sodium nickel chloride electrode materials that goes back to the 80s, and it's called Zebra because it's the Zeolite Battery Research Africa project out of South Africa. So this is already pretty mature technology that's out there. So we come back to it and we think, okay, well, these are really good for grid storage type technologies. right? There's already deployed sites of, over 200 sites in the last 20 years, provides gigawatts worth of energy and, hundreds of megawatts for power. So how do we translate this and understand this type of chemistry to design new sodium ion battery materials? Okay. Well, we look back to this, to just the fundamental properties of the sodium ions themselves, right? We talked about in the first lecture how sodium ions are different. We talked about understanding crystal structure. And so here we look at some of the differences. Sodium is more dense. You don't get as much capacity out relative to that of sodium versus lithium metal. The reduction potential is a little bit less, which is, an improvement. Atomic size, we said, that's bigger. We also talked about the ionic size with the same coordination number. So it's a little bit different. So already, the crystal structure of the host cathode material is going to have to change. It's going to have to be enlarged a little bit. And also the bonding sites, sodium tends to sit at the octahedral and prismatic sites versus lithium. Lithium ions sit at the octahedral and tetrahedral sites, so the bonding is going to be different, which will change our chemistry. And something we've talked about, as a driving force, the cost and the earth abundance for, investigating new sodium ion battery materials. In terms of what's already out there, in terms of the cathode, a lot has been done, right? And you could see here for the layered type materials, what you see is this P2 layered type material, O3 type material, where you have a mixture of nickel and iron substituting for cobalt. Because if you're translating from, let's say, lithium-ion battery technologies, you try to build up and translate what you've understood for lithium-ion battery materials design to that of sodium-ion battery materials design. And it's not always one-to-one, because based on what we just looked at, right, the sodium ions sit at both the octahedral site and the prismatic site. So clearly, when ions are interpolated and extracted, the local chemistry and the local structure is going to change, which will then also change how the crystal structure changes overall in the active material. Okay. So in terms of focusing on one family of compounds so that we're not all over the place, because there are a lot of materials to talk about, I'll focus on the layered materials. Because one, you could see in terms of competing with lithium-ion batteries with LMO as the cathode and graphite as the anode, you see that the layered materials really dominate, and compete with, in terms of driving up the average voltage as well as increasing the energy, the gravimetric capacity that's on the x-axis here. Okay. So let's talk about layered materials yet again. Here you see, we'll focus on the NaMO2 type structure, specifically, replacing manganese with that of nickel and iron. Capacity wise, somewhat competitive at 190 milliamp hour per gram of active material. The average voltage is, relative to sodium plus is 3.1. So that's, pretty competitive, pretty high. Although the voltage window is really large because that's just average. So what you see here are the different types of structures that the NaMO2 type of family of compounds can take. So you can see the crystal structure, this what's called the O3 type, and that's where sodium ions sit in the octahedral sites as outlined in the little yellow octahedron schematic here. Now, as sodium ions are, going in and out, it could also have, it could also sit in the prismatic site or the P3 type structure. In terms of synthesis, you can also synthesize layered compounds where the oxygen ion, or sorry, the sodium ions can sit in this octahedral site, but then also occupy this a different prismatic site. And depending on the synthetic conditions, you can have your compound, sort of go in between the O2 and P2 sites. Oh, okay. So we'll talk about, the cycling of these materials next time, but the rich chemistry of sodium-ion battery materials that are layered is going to be the foundation of like what drives substitution of the cation in these types of cathode materials. So with that, we'll adjourn